Welcome to the video presentation on HT distribution network breakdown maintenance, possible faults, identification and rectification. Here, we will learn how the HT distribution network is maintained from sub-transmission, that is, from 66 kV lines to 11 kV. Hello, I am R.K. Sharma, working as Head of Sub-Transmission Group in TPPDL. Sub-transmission network comprises 66 kV, 33 kV and 11 kV network in a distribution company. The main causes for faults in HT distribution network are overcurrent, overvoltage, external agency, accident, natural disasters like storm, cyclone, rain, dew, snow, and so on. The faults in HT system network can be classified in 4 components. They are transformer, switch gears, underground lines or overhead lines. Let us first discuss transformer. This is power transformer which converts 33 kV and 66 kV line to 11 kV. The 11 kV line is further distributed to feed the area with 11 kV distribution and connected with 11 kV distribution transformers or DT. You may see all the components and accessories of the transformer here. This is 11 kV, 250 kVA distribution transformer installed outdoors in the substation yard. Let us see the common breakdowns that occur in transformers. A tree has fallen on the plinth mount transformer and physically has damaged the HT bushings, jumpers, etc. A cat is trapped on the live wires and got electrocuted. HT bushings are made of porcelain. They are brittle and are commonly damaged due to exposure and variations in temperature as shown. The following images show their replacement. Following the cases of oil leakage from various points of transformer, oil leakage from valve and their remedial measures, leakage from valve before and after, leakage from tap changer before and after. Oil leakage is not arrested by M-seal on sockets due to variation of oil temperature. Always replace the socket plugs as shown. In similar lines, the gaskets used to plug the oil leakage deteriorate with time due to UV effect. They require periodical replacement. The images of before and after replacement are shown at LT bushings, at oil level indicator, at HT bushing collar. Oil leakage on transformer. Let us now learn about identification of defects in transformers and their remedies. HV, LV bushing. Check bushings for cracks, chippings, overheating marks, flashover marks and replace the affected bushing. For oil leakage, use tight oil seal caps and gaskets. Don't apply M-seal on HV, LV bushing to stop oil leakage as this may cause flashover. Oil leakage from top plate can be addressed by tightening nuts and bolts diagonally. Replace gasket if required. Palm connector surface pitted due to loose connection. Breather. Pink silica gel should be replaced by blue gel. After filling silica gel, breather should be tightened properly. Inside view of conservator tank. Due to improper coupling of breather bottle and flange, breathing points may be formed, thereby creating a passage for moisture. This leads to condensation and rusting of the conservator tank from inside. Conservator tank and oil gauge. Explosion vent diaphragm. Check the diaphragm. If it is torn, replace it by a new one. IR value test with insulation tester. Check the IR value of the DT HT to LT, HT to earth and LT to earth. Minimum value should be 50 m-omega. Let us see the faults that occur in HT switch gears. Switch gears occasionally flash or burst on account of short circuit current. These carbonizes its terminals or bus chamber, causing delay in tripping mechanism. Flash in RMU cable chamber, complete chamber becomes carbonized. The OCB tripped and flash has occurred at its cable termination due to short circuit in outgoing cable. Faulty cable is disconnected from switchgear. Let us now learn about types of faults in yard, switchgear and their maintenance in detail. Switchgears commonly used are OCB, vacuum and SF6. See the healthy state of outdoor RMU having two isolators on the sides of circuit breaker. Hotspot at palm top conductor's bus bar. Hotspot at circuit breaker connection. Hotspot at joints. Control and relay panel for 35 kV switch yard. 11 kV switchgear panel. 33 kV circuit breaker. 11 kV vacuum circuit breaker. Factors affecting switchgear life. Pollution. It mainly affects the insulation properties of insulators along with deterioration of metallic parts, corrosion of the equipment installed in industrial areas or near drains which generate acidic fumes. Climate. It also affects the insulation of the equipment if the equipment is installed in humid conditions. Major impact will be on insulators if space heaters are not on. Loading of equipment. If equipment is loaded within safe loading conditions, it will have good lifespan. If equipment is underloaded or overloaded, the life of equipment deteriorates. Maintenance practices. Maintenance practices play a major and crucial role in determining the life of equipment. On one side, good maintenance practices enhance the lifespan of equipment. On the other side, improper maintenance practices deteriorate the equipment lifespan. Thermal imaging. In this technique, a thermal imaging camera is used. Thermal cameras detect the changes in heat in the area at which they are pointed. The device can use these variations in heat to build a picture on a screen. These devices are fast becoming an essential tool for preventative maintenance work. This is because they show where heat is leaking from pipes or where electrical equipment is giving off more heat than it should. For example, in the case of using a thermal imaging camera for circuit breakers, the technician would point the device at all the circuit breakers. If the resulting image on the screen suggests that a high amount of heat is being generated from a specific breaker, then it may indicate that there is some damage. The cost for replacing the breaker at this point will be small. However, if the issue will be left unaddressed for an extended period, it will lead to major damage of equipment. Thereby, costs will increase. Hello, I am Amrendra Kumar, Zonal Manager of Zone 571 of Tata Power. I will tell you about switch gears installed in 11 kV substation. This is RMU or ringman unit having 2 LBs or load break switch and 2 circuit breakers. These are SF6 circuit breakers. This is gas manometer which shows the gas pressure. Here the pointer is indicating on green field showing arc quenching medium of SF6 gas is fully pressurized. Thus, it can be operated for on or off. However, in case of low pressure, when pointer is in the red field, the switch cannot be operated. Further, there is a voltage presence indicator system VPIS, which gives an indication if the bus bar is charged. The 3 LEDs are for the 3 phases and show that the RMU is charged and all phases are energized. The isolator has a switch which makes or breaks a circuit. An earth switch is provided for checking the system. In this sub-transmission group, Many expert technicians and engineers take care of the network issues. There will be many faults happening as the HT network of any power distribution company is always big. Faults in underground cables are a major challenge for a utility like TPPDL. Cable faults have become very common as many civic agencies work for development projects. Excavation is an integral part. Water and sewage lines, optic fiber, communication and gas pipeline works. All these agencies damage our cables during digging activities. We need to get them repaired within 12 to 18 hours. We have fault locating vans, FLC. These FLC vans pinpoint the exact location of fault in underground cable. Using this technology, we identify the faults and repair those cables. We repair straight-through faults by jointing cables through straight-through joint boxes. When there is a problem in a power transformer, we handle them very well. The technicians are experts in repairing the transformers on the site. They are assigned such tasks to check power transformers and repair minor faults on the site. In transformers, problems such as dissolved gas analysis, DGA, are handled by in-house people with the help of the available tools and tackles, including testing equipment. We rectify faults of power transformers. Let us look at the underground cable faults and their rectification. This is a fault locating van equipped with all gadgets, which pinpoint the location of fault in underground cables. This is the instrument indicator, which pinpoints the fault with beep sound on the earphone for exact location beneath the ground. Look closely at this instrument, which pinpoints the correct location of a faulty cable. Cable testing, fault location and recording using compact system. About compact system. Compact system is one of the latest technologies of self-contained cable testing system. It is encased in a small instrument with relatively light and computer-aided system. Exact pre-location new method introduced, that is ARM+. Easy for testing, adjusting surge voltages and time. Compact system. About cables. There is now considerable preference for UG cables or OH lines. In metropolitan cities, it is not feasible to have transmission and distribution with OH lines due to non-availability of land for constructing OH lines. OH lines mar the aesthetic value of a city's skyline. On the other hand, UG system is preferred as it is unaffected by abnormal weather conditions, storms, tree falling, trees touching, snowfalls and foreign objects. Causes for cable faults: mechanical damage, damaging of sheath or insulation, external agents, sheath corrosion due to chemical action, vibration due to heavy traffic on road, thermal damage, increase in thermal resistance of soil, operational problems, cable deterioration due to overloading, joint deterioration, migration of semi-fluid compounds from joints, electrical tracking along the insulation owing to poor stress control, terminal defects, poor workmanship, joints, manufacturing defects, cracked lead sheath. Testing. IR measurement. IR measurement is done by using MEGGER. Megger. By using megger. Face-to-face and face-to-ground is tested using 5 kV megger for 1 minute or till reading stabilizes. Minute IR value for healthy face is 50 m-ohm, 11 kV, 100 m-ohm, 33 kV, 500 m-ohm, 66 kV. HVDC testing. High voltage DC testing, pressure testing is done only after IR values are not found satisfactory. Each phase is tested for 5 minutes with regard to ground and other phases grounded at 6.5 kV, 11 kV cable, 19.5 kV, 33 kV, 38 kV, 66 kV. The leakage current pattern is observed during the testing period shown graphically in compact system. If the leakage current has a rising trend, the cable is faulty, and if there is downward trend, cable may be healthy. By testing, faulty phase or phases is detected. Let us see the instruments of the FLC van and their functions for pinpointing of faults. HT cable fault on the pavement. The cable is damaged by some other utility while laying RCC Hume pipe for storm water line. Pit has been dug to prepare new cable joint. New HT cable joint is prepared in a trench. You may see that the cable end is placed over an RCC docket. A 75 cm 3-inch sand bed is prepared below and above the cable joint. Then it is covered with RCC docket and brick lining to protect it from mechanical damage. After completion of docketing, a root marker is placed before refilling the trench with soil. The common instruments used to identify faults in HT system are Mega to test insulation, Hypot to test voltage sustainability of cable, Thermovision camera to test hidden weak joints or links, and FLC van. Let us look at a fault in ABC, air bunch conductor cable. This is due to corona discharge in 11 kV ABC cable. The cause for fault is that the metallic screens of ABC cable are not grounded at the end terminations. Induced voltage develops at the sheath of ABC. Thus, it causes short circuit and gets damaged. It is mandatory to ground messenger wire with proper earthing. My name is Rajesh Jaiswal. We have come to replace a faulty HT AB cable. You can see the AB cable leads are burnt at the center due to an electrical fault. A new AB cable is prepared of a length equal to span, that is, the distance between poles. On both sides of cable, piece cable ends are prepared and punched with sockets of correct rating. Now, you may see that the lineman is replacing it with new HT ABC cable. He has been jointed to the messenger wire at both ends. The jumpers are connected to it at both ends of pole. Let us look at overhead system faults and their rectification. HT overhead system is most vulnerable to storms, cyclones, floods and heavy rains, especially in rural area. This is because uprooting of trees is common in these areas. Hence, overhead networks are susceptible to line leakage in case of improper protection. Here are glimpses of such occurrences. Here, a tree has fallen on the HT lines. See the stress on conductors. Further, delay in removing the tree will snap the conductor due to strong winds. Here, due to a fallen tree, HT lines got damaged and snapped. The conductors are lying on the ground. Here, a PCC pole carrying HT ABC line is uprooted from ground and is leaning towards trees. It needs immediate replacement. This is because electric supply will be affected to the whole area. The branch of tree damaged the HT line from top hamper. Pin insulator is tilting to one side. Lineman is climbing the pole to remove the broken branch and refit the pin insulator. Here, the uprooted pole is being replaced with conventional system. You may see ropes are tied at the upper portion of PCC poles and pulled up as anchor to erect the new pole. Lineman is shifting the accessories, eye hook, messenger wire and cable from the broken pole to the newly erected pole. This is a flood-affected area where all HT lines and poles were damaged. New poles are being erected and lines are being shifted to the new structure. Here, you can see that A crane has lifted the broken part of PCC from DP structure. Closely observe the process of removing HT disc insulators and other accessories on DP structure. Always ensure that after erecting a new pole, it should be grounded and the plinth should be prepared with cement mortar. This is HT overhead line going across the road of an industrial area with movement of heavy-duty vehicles. You can see that the height of lowest conductor earth guard wire from ground is more than 5.5 meters as per CEA regulations. Further, the guard wires are firmly tight at both ends so that line conductors may not touch ground. In this video presentation, we have learnt how HT distribution network breakdowns occur, how the faults are identified, how they are rectified and details of instruments used for testing.